Okay, so let's say we have a particle of charge Q sitting at some location, and we want to find the divergence of the electric field everywhere. So, of course, Gauss's law in differential form tells us that this divergence is proportional to the charge density, and so the charge density is zero everywhere except at this point. And that looks like a somewhat weird, strange function, because all the mass, all the charge is at this one point in space. And so the notion of a charge density, some charge distributed over volume, is somewhat tricky. But we'll see that this thing is obviously zero everywhere except here, and at that point there, it's going to become infinite. So if we want to go through this part to get it, let's see what that looks like. We need the electric field. We know what the electric field of a point particle is. Of course, we could also use Gauss's law in integral form to find that. So we would integrate over a sphere of radius r, so that this side would be e times 4 pi r squared, and this side would be the charge inside, and all of the imaginary spheres would have charge q inside, and then we would divide by epsilon naught, and so we would have that the electric field, right, in magnitude is q over 4 pi epsilon naught r squared, which we already know, and then we'll make it a vector, and so r hat in spherical coordinates. And so we want to evaluate this quantity using spherical coordinates. So what is the divergence in spherical coordinates? We only have a radial component, so we know that that's going to reduce to 1 over r squared times d by dr of r squared times the radial component. Right, so in this case, let's put this in. We know what that is. It's this. So we have a q over 4 pi epsilon naught, right? There's a constant there. Then we have this r squared. And then we have d by dr of r squared times times the part of ER that's left, because most of it is out there, and that just has 1 over r squared, so this becomes a 1. Right, and so we're tempted to just look at this and say this is 0. Well, but we want to be careful, because it's 0 if r is greater than 0, but we have an issue here at r equals 0. So at r equals 0, this blows up, and it blows up fast as r squared, and so that's where we get our infinity. So we can see that the divergence, in fact, is 0 everywhere except at the point where the charge is, which makes the divergence blow up.